Okay, so let's establish a baseline for our environment. We're going to need Git, Visual Studio, and Vcpkg, and we'll get our libraries, C++ libraries from Vcpkg. I'll walk you through that process. Open up a command prompt and clone the library anywhere. I have it in root at C, but the location doesn't matter. It can be anywhere. That command fails for me because I already have it, but once you get it, cd into it and run the bootstrap file. The next command, vcpkg integrate install, lets Visual Studio know where it can find the vcpkg libraries. And finally, we can get our libraries now. We're going to need Boost, ZeroMQ with sodium, that's important for encryption, Protobuf, CPP Zmq, nlom on Json, and Bond. I'll have this command linked in the description below. You can just copy and paste it. I'd recommend getting both x86 and x64 versions. Sometimes, depending on what you're working on in Visual Studio, it can be confusing if you can't find the right library. So I'd recommend getting both. And this command will take a while. So grab a Red Bull or a coffee, and once that's done, we can rock and roll. Let's write our first example. This will be a request reply example. We're going to send a number from request to the reply socket, and we'll return the square of that number. Now, if you've properly installed the libraries via Vcpkg and you've done Vcpkg integrate install and you're matching the bit versions, I'm in x64 there, and I have the x64 libraries installed, you'll be able to find Zmq addon.hpp. Note that the context is global. Typically, context can be shared and should be shared, but there are situations where you're not going to share the context. Contexts are used to derive sockets. Okay, so there we derive a request socket from the global context, and then we connect that socket over TCP to endpoint 5555. Note the word connect there. Then in our event loop, all we're going to do is generate a random number, implement a bit of a speed bump in there. That's why I'm getting the chrono library in there. We don't want to overwhelm the reply side, and also we want to see what's going on. So a tiny 100 millisecond speed bump there. Pull in random. So here we'll generate a random integer and convert it to a string. Then we're going to create a Zmq message from that string, and then we can send it out over the socket. Now, typically you'll have some kind of a serialization mechanism there. At a minimum, you'll have Json, but usually in production environments, you're going to have some kind of a binary serialization thing going on, like Protobuf or Microsoft Bond, which we're going to take a look at later in this series. Now, the important thing to note here is that the send must be followed up by a receive. You can have multiple sends with multi-part messaging here, but for a request socket, you must finish it off with a receive. It is implemented as some kind of a finite state machine, so to complete that cycle, the receive must be there after a send. You cannot have a series of sends with never receiving. And the same is true for the reply socket, but in a different order. The receive on the reply side must be followed by a send, and you'll see that in a bit. So all we're doing here is generating a random integer, converting it to a string, putting it into a Zmq buffer, sending it over the socket, and waiting for a message in return. Now I have a bit of a typo in there. I have zout toString view. You have to be careful with messages after they're sent out. So Zmq messages, after they've been sent out, the guts are removed from them. So there's nothing in there anymore. Okay, Zmq messages, Zmq sockets, and Zmq contexts are movable. So you have to be careful with them. So consider messages, Zmq messages, after they've been sent, those objects, you need to consider them stale. On the server side, the mechanics are quite similar. Instead of a request socket, we have a reply socket, but notice that we're binding the reply socket. And this is a Zmq convention. Client sockets are connected, server-side sockets are binded. Okay, and that is not always clear in a lot of scenarios. So over time, you develop an understanding of which sockets are connected and which sockets are binded. Now the receive command is a blocking command. And when we start this application, the server-side application with the reply socket, it's going to block on receive until it receives a message from the client. And to reiterate, the reply socket, to complete the cycle, after a receive, you must do a send. Let's start up the server-side application first. And you can see that the information is being returned. Just to make things more explicit that activity is going on the reply side, let's have something get printed out on the server side, the reply side as well. If you enjoyed this video, consider subscribing and hit the like button. Thank you. Now let's take a look at a situation where the reply socket is connected to multiple peers. And the point of this example is to show that the reply socket can not only be connected to multiple peers, but it can only respond to the socket that sent it the message. So in this modified scenario, we're running two threads of request sockets, each sending their own calculation requests, and they get back the correct answer. So this is where we left off last time. And the only change we will make here is we'll take the contents of the main function and simply run it in two threads. That is the only real change we're going to make here. And there you have it. The reply threads are, the request threads are receiving the correct responses. A very quick word on Json. Going forward, we are going to be sending messages back and forth using Json. Actually, we'll be sending strings, but in the applications themselves on both sides, we're going to take JSON objects and either parsing them from the ZeroMQ buffers or turning them into ZeroMQ buffers. And it's really quite straightforward. You can observe how that's done on the sending side and how it's parsed on the receiving side. A A thing I'll mention is that your data that is being sent back and forth between these processes is in the clear. It's not encrypted. And if you have Wireshark installed, you can actually see the packets going back and forth. As in this case, they're raw strings, but by default, ZeroMQ does not encrypt your messages. It can encrypt messages, and that is why when we pulled in ZeroMQ, we installed the ZeroMQ sodium because ZeroMQ can use sodium to do curve encryption, and we're going to take a look at that later on in this series. I made a video on closing sockets and destroying contexts, but it turned out to be a much more trickier topic than I had anticipated.
This could be a lot more complex.
So I'll leave that for another day. But just to recap what we've done so far, um, the important things that I'll mention are that request and reply sockets are implemented as finite state machines. In a request socket, a send or a multi-part send must be followed up with a receive, and in a reply socket, a receive or a multi-part receive must be followed up by a send. Otherwise, the socket will error out. The next thing we learned is that reply sockets can only respond to the socket that sent the message. 3, request sockets connect, reply sockets bind. 4, it's recommended to close sockets and destroy contexts. Maybe we'll do that another day. It's going to be a longer video. 5, at a minimum, Json should be used, but a preference should be given to binary serialization, which we'll cover later on. And finally, data by default is sent in the clear. It is not encrypted, but it can be encrypted, and we're going to take a look at that later on as well. Now let's quickly take a look at the exclusive pair pattern. Here you have 2 pair sockets, and what's special about these is that there can be no third socket connected. No third socket can enter the game. And this is often used as a sort of a signaling mechanism. Another thing worth mentioning is that remember how in request and reply sockets you needed to do both either a send and receive, or receive and a send. Here you don't have to do that. You can just keep on sending or keep on receiving. So here I am just starting out 2 new C++17 projects side by side, and doing what we did with the other examples, declaring a context, deriving the socket, connecting to it, generating some random numbers, creating a JSON object, dumping it to a string, putting it into a Zmq buffer, and sending it over a socket. I have a 500 millisecond speed bump there, just so we can observe. And notice that on the left, there's no receive command. The socket just sends. And on the right, I have a receive and I'll have a send. So you have more flexibility that way. So that's the exclusive pair pattern. Not very exciting, but can be very useful. For experimentation's sake, let's see what happens when we try to connect a third socket to an existing pair that's already in communication. What do you think happens? Will we see an error? Will we see blocking behavior? Or will they actually connect and communicate even? So let's run the same function basically but in two separate threads. I'll put a small speed bump in there to make sure that thread 0 connects, or the socket in thread 0 connects. And we'll send some identifier along with the JSON payload, just so we know the messages that are going through on the other side. So it looks like when the first pair connect, they communicate fine. The second socket actually tries sending messages, but they're not received on the other side. So with pair sockets, we can send and or receive. There's no need to close the loop like we did with request and reply sockets, where you needed to have a send and receive, or receive and a send. Let's now take a look at the push-pull pattern. This is a pattern where the data flows downstream. The push sockets have no ability to receive messages. This is also known as a producer-consumer pattern, where the consumer can only send messages downstream. Now, the other thing to keep in mind is that the messages are fair queued. Let's say you have a push socket with 3 messages to send to 3 sockets. Each socket will receive 1 message. Okay, that message M1 will not get duplicated. Only one pull socket will receive M1, only one socket will receive M2, and only one pull socket will receive M3. Let's see what that diagram looks like in practice. We'll have 2 Visual Studio projects, and we'll have 3 pull sockets running in separate threads, and 1 push socket that'll be sending messages. And as you can see, the iteration numbers are unique. None of them are duplicated. And the messages are being distributed fairly. Let's now take a look at the publish subscribe pattern. This is just a basic broadcast pattern where a publisher just broadcasts messages under different topics, and the subscribers can be subscribed to either everything that's being published, or they can subscribe to specific names that are being published. Another important thing to keep in mind is that the publisher doesn't care whether or not any subscriber is online. It's almost like the radio. The radio station doesn't care if any specific individual is out there listening or not listening. There's also something known as Zmq Conflate, and if you have that socket option set, the subscriber gets only the latest message, and this is useful in scenarios where you have a slow consumer, or a consumer that is interested in only the latest information that's being published by the publisher. So we are going to take a look at PubSub. Let's do the usual. Let's start off with two Visual Studio projects, both C++17. Let's get our imports, create a context, derive a socket, and generate some random numbers. What we'll do is, with equal probability, generate a price change for AMD, Intel, and Apple. And just to play along, assume that the norm dist is some percentage price delta. So this is a multi-part message. The first part is the topic, and the second part is the payload. On the subscriber side, we subscribe to Intel and AMD only. We ignore Apple. And we print out both the topic and the payload. So as you can see on the left, 3 names are being published. On the right, 2 are subscribed to. So that is plain old vanilla PubSub. Now let's look at how we can switch subscriptions at runtime. So on the right there, we're already subscribed to Intel and AMD, and on the 50th iteration, we will switch our subscriptions to Apple only. I think my brain was fried there for a second, so it was a bit of a typo. But on the 50th iteration, we will unsubscribe to the existing topics and subscribe to the new topic, Apple. right, now let's examine the output. As you can see, we're subscribed to Intel and AMD, and on the 50th iteration, only Apple is being published. Let's now talk about the last message only option. You can have situations where your analytics module, let's say, can't keep up with your data feed. Let's say, at certain times during the day, information comes out. Let's say non-farm payrolls in the morning. When it comes out, you get this intense sort of burst of information, and you have to sort of make a decision on the subscriber side. And what typically happens is you create some kind of like a coarse grid, some kind of a circular buffer, and you make sure that at the endpoints on that grid, the data is accurate, but you're not interested in any of the intermediate values. So the way you do that is you simply subscribe to only the latest messages and construct that grid or construct that circular buffer, whatever it is you have. And in ZMQ, that is known as the conflate option. Now, with the conflate option, your multi-part messages don't work. Okay, so that means your subscribers, your topics, you won't have any more topics to subscribe to. Because remember, on the publisher side, topics are the first part of a two-part message. That entire payload is a two-part payload. The first part is the topic, the second part is the actual payload. So you don't have any more of that. Let's run it. See what we get. I think the subscriptions weren't set. So in this case, you have to set a command for blanket subscriptions, which is right there. Now notice that the iterations on the right, the latest iteration on the right is current with the latest iteration on the left, and any intermediate values are considered stale and discarded. We had a bit of a bug in the last program we wrote. On the publisher side, we were sending topic and payload messages, even though the conflate option was set on the subscriber side. In this case, the topic itself was actually a payload. So in each iteration of that while loop, we were sending two payloads to the subscriber. And to show you what's going on, I'll modify the output. And there you can see that what was the topic previously is now a full on payload. So the moral of the story here is that, with a lot of these settings with ZeroMQ, you sort of have to be careful with what you're getting into. They can have these weird sort of effects in your program where things start behaving a bit strangely if you're not careful, and that just comes with time and making enough mistakes. If you enjoyed this video, consider subscribing and hit the like button. Thank you. Now let's take a look at dealer and router sockets and the dealer router pattern. So we looked at the request reply sockets. The request sockets sent requests to the reply sockets, and the reply socket had no choice of whether or not it wanted to send back a response or whether it wanted to send a response to a different socket. Well, dealer and router sockets are very different than that. Dealer sockets can send requests and they can obviously receive messages, but what's special about dealer sockets is that they do not have to follow the send and receive cycle. They can keep sending or they can keep receiving. Router sockets are even more powerful in that router sockets track the identities of the sockets that send them messages. And the router can, as the name suggests, route the messages wherever it wants. So you can have these incredibly complex patterns emerge with the dealer and router sockets. So for example, you can have a trading strategy A dealer, trading strategy B dealer that send messages to the router, and then the router sends that message to let's say some kind of a hedging dealer, and then you have an execution dealer, and you can hook all these up, and you can get these very incredibly complex patterns with dealer and router sockets. Now, I am hesitating to use the word asynchronous mechanisms because you can get asynchronous behavior with the existing sockets that we've seen if you use the polar, and we will look at the polar later on. But for now, the way to look at dealer and router sockets is in terms of patterns rather than synchronicity or asynchronicity. Okay, the patterns are fundamentally much more powerful than the sockets that we've seen before. Let's first get a basic example running. I'm going to create two Visual Studio projects, both C++17. Set up the text side by side, grab the imports, create a dealer socket, connect it to 5555, and in this case, dealer sockets connect and router sockets will bind. And remember, it's the stronger socket that binds, the server socket binds, although that's not always clear in certain cases. We'll generate some random numbers, create a JSON payload, dump it to a string and into a Z buffer, and send it. Then we create a router socket, bind it to 5555, listen for a message, and that ZMQ receive multipart is actually a part of ZMQ underscore add-on. If you're using zmq.hpp, you won't find that there. So that's why we've been using this. So there you see the messages being delivered router side, and what you'll notice is that they are multipart messages. Ignore the true. The true is the return condition that we're printing out. But for each iteration, you see that there is a default message identity, and then the payload. So the router assigns a default identity to every socket that it receives a message from. We can also assign custom identities so that it's more understandable by humans. In real pipelines, you want to sort of be able to reason about the flow of information, how the system is wired up. So it helps to have sort of human understandable identities on each socket. And there's a ZMQ identity tag on a set socket option. You have to set that before you connect. And now router side, the identity is strat A. Just to make this idea more concrete, we are going to look at another dealer router example where we have two dealers, strat A and strat B. Strat A is going to send a message to the router socket, and the router socket is going to send that message to dealer B. Now, your imagination can take this as far as it needs to be. You can have dealers to dealers, you can have routers to routers, you can have dealers to routers, and uh, it's really whatever you can imagine with this, you can pretty much do. Dealer and router sockets completely change the game, and just a limited example I thought would be helpful to show. Here we're starting off with the example from last time. We're going to take the contents of our main function and create two threads. The first thread of strat A is going to be a sender thread, and the second thread is going to be a receiver. A thing to note here is that unlike the request and reply sockets, you can keep sending on dealer sockets or keep receiving on dealer sockets. There is no need to complete the send receive cycle like we did with the request and reply sockets. And as a side note, the reason we're using the ZMQ underscore add-on header and not the zmq.hpp header is because that ZMQ : receive multipart function, that is part of the ZMQ underscore add-on header, which actually itself includes a zmq.hpp header. And there you have it. Messages from strat A are being routed to strat B. Pretty straightforward. Now let's take a look at something called a poller. And there are two versions of this primarily. One is called a Pollin and the other is called a Pollout. Now for the Pollin checks for the socket's readiness to be read from, and the Pollout checks for the readiness of the socket to write to. So the Pollin typically is meant for the receiving side of your application, and the Pollout is meant for the sending side of your application. Now, why is this important? The primary thing is efficiency. Now, if you want asynchronicity in your applications by having multiple sockets in a single thread, you can actually do that. You don't need the poller. You can check for return conditions on each socket, and depending on true or false, you can go forward in your execution flow. Because typically, remember, the receiving methods are mostly blocking. So you have to be careful with how you handle asynchronous behavior in those sockets if you are not using the poller. What ends up happening is that one of two things. You either spend a lot of CPU cycles constantly checking for these return conditions and proceeding with the event loop, and your CPU just goes full throttle, or you end up putting some kind of a 1 millisecond or a 2 millisecond speed bump to sort of cool down that CPU usage. But then that's not efficient either, right? The 1 or 2 milliseconds for a CPU is an eternity, and it's actually not even 1 or 2 milliseconds. It's actually probably much more, some non-deterministic amount, probably 10, 15, 20 milliseconds each time. So it's not very efficient to go about things that way. So that's why we need the poller, and specifically on the receiving side, the Pollin. We have multiple sockets. The poller tells us, hey, socket 1 is ready to be read from. You read from socket 1 and go back to the poller. And the poller is what is the blocking call, not the individual sockets themselves. And with the poller, you can have infinite block. You can have 0, which is immediately times out and gives you a return condition. And you can have, a specified, user specified 1 or 2 or 5 milliseconds, whatever you want, of a timeout. So it's very versatile. You can use it in many different ways. And, also it helps if you have other things to do. Let's say receiving is not the only thing you're doing. You're taking care of other peripheral issues. Let's say every 1 second, so you can have a timeout on the poller itself. But we're going to look at that shortly. So on the sending side here, we have 2 push sockets with equal probability. We are going to send a message on one of them. We'll implement a small speed bump there. On the receiving side, we'll have 2 pull sockets on 555 and 5556. And inside the event loop, by default, this will be blocking. Okay, I'll show you that the execution in this event loop is not going to proceed because one of the receive sockets is going to be waiting on a message that never ends up arriving. Because the execution flow is blocked on the other socket. There, it's the receiving side is basically stuck at that point. Now, the naive way of fixing that is to put in a receive flag, don't wait, and check for the return conditions. Now, if you don't check the return condition itself, it's simply going to be an infinite loop at this point. Okay? So the return condition here is a stood optional, and you can check if it has a value or if it doesn't have a value. If it has a value, you can extract the message. So now your program on the receiving side is asynchronous, but there's a problem with this. If you look at the CPU usage for that program, it's going to be incredibly high because you're constantly in that event loop. You're checking. So my screen recording software is probably around 25%, and additional 20% is being taken up by that Pollin underscore poll.exe. And obviously that's not a good sign. You cannot have realistic applications take that much CPU for basically nothing. A way of fixing this is a bit of a hack. You can put in a small speed bump, let's say a 1 millisecond speed bump. But that 1 millisecond speed bump is not actually a 1 millisecond speed bump. It's much larger than that. And it's some non-deterministic amount. So if you run it again, same result as before. But if you look at the CPU usage, it's much lower, and that CPU usage is just a screen recording software. Okay, so that's taking up next to no CPU power, but you've handicapped yourself in a different way. You've limited the amount of times you can go through that event loop because you have a speed bump in there, right? It's a fixed speed bump that limits the amount of times that you can receive a message in a limited amount of time. It's not truly asynchronous. So let's call that dirty, and let's now do it the proper way, the clean way. And the clean way is to get the poller and use the poller to check the read conditions on the sockets. So you have a socket, file descriptor, and a flag. Do that for both. You're telling the poller you're interested in poll-in events. Now, the important thing to note here is that The blocking section now is that ZMQ poll inside the while loop. Okay, and that -1 says that's an infinite block. Do not proceed until a message has been received on one of the sockets. If a message is received, then you check the events and proceed with execution flow. This now is a properly done asynchronous program. And again, disregarding the OBS screen recorder, the CPU usage for this will be next to nothing. And this is how you check for events that are received on the sockets and retrieved only when they exist. Okay, so that is poll in. Next, we're going to take a look at poll out. Now let's take a look at poll outs. And poll outs are meant for the sending side of your applications. They check whether or not the file descriptor can be written to. If it can, then the message is sent. If it cannot, then you can handle that return condition. Now, at first glance, it might seem overkill, especially considering this simple example. We'll have a dealer and a router, and the dealer socket is going to overwhelm the router socket, and we're going to have a return condition that will get printed out. But in real applications, you're going to have really complex topologies, and it's next to impossible to predict how or where the packet convoys are going to form, where the slowdowns are in that topology, or if you get a sudden burst on a certain socket in your application. It's very difficult to predict. So you need some reliable reliability check in your applications on the sending side. And this is also useful for applications where the packets are expensive to generate. You don't want to waste the resources used to generating those packets. So poll outs help you build a topology that is resilient and helps your application perform the way you think it should perform. Okay, so like in the poll in example, the mechanics are similar. You'll have a list of items in your poll item array, your sockets in your poll item array, and you're simply going to check the return condition on ZMQ poll. And if it's true, that means you can send the message. If it's false, that means you cannot send the message. And the same thing there, you have -1 for infinite blocking, positive value is a millisecond timeout, and 0 is immediate return. So the ones that are being printed out means that messages can be sent, and as soon as that turns to 0, that says the Pollout says, hey, the socket is not ready to receive messages. So this way you prevent tripping the high water marks on your sockets or dropping messages on your sockets. And to reiterate, it doesn't really make a lot of sense in this contrived simple example, but if you have this planned out in your entire application throughout your entire network topology, it really does make a difference. So that is the Pollout. Now let's take a look at binary serialization. Thus far, we've been sending messages back and forth using strings and Json, but that really doesn't enforce a contract between the communicating parties. You could, as a programmer, go in, arbitrarily change a variable name in JSON or restructure JSON, and parsing that on the client side then becomes very sort of ad hoc. And you have to sort of plan things out and how plan for failures and how variable names change. And it's just a very dirty way of doing things. But what binary serialization allows you to do is just send blobs of ones and zeros, while at the same time enforcing a contract on the two communicating parties. Not only is it more efficient, but it promotes correctness. So you'll have a tool, compiler, like a Protobuf compiler or a Bond compiler or a flat buffers compiler, and you will generate a set of C++ or Python or Java or .NET code. Okay, so the compiler will generate code. You will import that code on both sides of your applications. So the sending side and the receiving side of your applications agree on this contract on how one side is going to be sending the messages and how the other side is going to be receiving the messages. And I think that performance is a secondary benefit, and the primary benefit is correctness. You want your programs to be correct before you worry about your programs being fast. And in this case, you get both. You get reliability and you get an order of magnitude speed up performance over JSON. And there are a ton of these libraries out there, Bond, Protobuf, flat buffers. There are a million others. And right now we're going to take a look at Protobuf, and in the next section we're going to take a look at Bond. So if you've used Vcpkg to install Protobuf, it should be in your Vcpkg folder. Under installed, you'll have different bit versions, and depending on your bit version, go into that directory. In the tools folder, you'll have Protobuf there, and you'll have a bunch of DLLs and an exe, and just simply copy the folder and place it alongside the current examples. And in actual applications, you can have this be a part of your build step where you generate or you run the Protobuf compiler before building the application. And we'll take an example from the documentation. It's simply a struct consisting of a string and two integers. Open up a new command prompt and run the Protobuf compiler. We'll tell it proto-c, cpp out, and give it the file name. Then you'll see a bunch of header and source files. Copy them and paste them in both projects. the sending side and also on the receiving side. Import them in Visual Studio. So we have a search result struct, 3 items in it. We get the number of bytes. Create a Z buffer. And we serialize directly into the ZMQ buffer. So there's no need to generate an intermediate string. Let's write in a tiny speed bump there. Receive the ZMQ message on the pull side and formulate the proto message directly from the Z buffer. There's no intermediate string being formed here either. And that is Protobuf. Really no big mystery to it. It's preferable to Json and definitely preferable to sending strings back and forth. So next we are going to look at Microsoft Bond. So let's now look at Microsoft Bond, which is an alternative to Protobuf. Now there's a huge amount of overlap between a lot of these libraries, but the reason I want to cover Microsoft Bond is because it's actually a very nice library for binary serialization, and it has certain features that that other libraries don't have. For example, you can partially inspect your serialized packet and build pipelines through it. It's called bonded. So what you can do is you can just peek at the packet and figure out what the type of the packet is and send it downstream without actually deserializing and reserializing the entire packet. And that is a phenomenal feature that Bond has, and it has a very, very powerful type system. In fact, it's better than a lot of the other competitors that are more popular. So there on the screen, you can see that you can get it the same way using Vcpkg, and we'll create 2 Visual Studio applications, and we'll do a dealer router example. Switch everything over to C++17. And what we'll do here is we'll create a bond file using that example from the documentation. Let's call it example.bond. Let's save it somewhere next to our projects. And the gbc.exe file, which you can find in Vcpkg, installed, Bond, x64, tools, you can simply get that gbc.exe and use it to generate your source files. Copy the source files into the project. And Bond supports C++, Java, and .NET. So once we've added the generated files, we'll take the example straight from the documentation. And first, just on the dealer side, what we'll do is we'll take the example here and we'll serialize and deserialize in the same application exactly the way they're doing. So that destination object will print out the dst.name. That's after the information has been serialized and deserialized. And there you see the deserialized string getting printed. Okay. Now what we'll do is we'll take the second half, post the serialize command there, we'll take the second half of that main and we'll switch it over to the router side. So it's exactly what we were doing before. But now we'll send the serialized contents over the dealer socket. And notice that in this virtual machine, I'm setting the router identity a bit differently. It's sock.set Zmq sockopt routing ID. And that's because this virtual machine has Zmq 4.7.0. On the other PC, we had an older version of Zmq 4.6. So there are some minor syntactic differences there. Next thing, what we do is we get the length of the bond buffer. We do a memcopy into a Zmq buffer and just do a sock.send zout. And on the receiving side, we simply create a router socket. Create a ZMQ message, receive the contents into that message, turn the ZMQ buffer into a bond input buffer, and deserialize that into the DST object. And there you go. The contents are received on the other end, and it's exactly the same example as the documentation, but over ZMQ. And I highly urge you guys to take a look at Bond and give it a chance. It might actually work better for you than Protobuf or some of the other alternatives. So now let's take a look at encryption over ZMQ. The reason we installed ZeroMQ with sodium is because ZMQ uses libsodium for curve encryption. And since we did that, we can now try and encrypt our traffic back and forth. In one of the previous examples, if you noticed, we looked at the traffic in Wireshark, and you could see that the traffic was being sent in the clear. So what we will do now is implement the simplest example we can of curve encryption, just as a starting point. So this example is not meant as the best example out there, but it is the most minimal example I could come up with that demonstrates curve encryption in ZeroMQ. What we'll have is, just as before, we'll have a program right there, a request and reply socket. The request socket sends an integer, and the reply socket sends back the square of that number. There's nothing special about this program. We've seen this multiple times before. But if you open up Wireshark, you'll see that the numbers that are being sent back and forth are in the clear. So you can see the data right there. We are going to try and encrypt this traffic. So we have two sides to this application. We have the client side and we have the server side. The first thing we're going to do is generate a curve key pair, server side. It's going to consist of a secret key and a public key. Next, we will create a server thread that serves up that public key to any peer that matches up with the password. And the pass will be, let's say, pass 123. We'll do a comparison, a string comparison, and if it is successful, we'll send back the server-side public key. Next, we'll take the server-side public key that we received in the client, and we'll generate a client key pair. Okay? And once we do that, the traffic will be encrypted. So this example is a straight up vanilla example that we're going to start off from. Nothing special about it. We've seen this a million times. The first thing we are going to do is, in the server-side application, we'll call a ZMQ curve key pair. And ZMQ curve key pair will generate a secret key and a public key. The ZMQ curve key pair returns a condition, success or failure. We'll check this for success or failure, and 1 indicates failure. If curve key pair generation is a failure, we'll exit the program. In a real program, you obviously don't want to shut down your server, public key server, so you'll have some alternative logic. But just as a demonstration here, just to keep things simple, we will exit this. Next, we'll create a thread that serves up this public key. Let's call it the P key server. And now let's write the public key server. This will run on socket 5555, and it'll be a plain old reply socket. Again, nothing special about this thread either. It's simply responding to correct passwords with a public key string. That is all it's doing. So we receive the password, compare it against pass123. If it's successful, return the public key. So that implementation is done of the reply server. Now on the client side, we'll write a function that goes and grabs that public key. Public key server is on 5555. We send the password pass123. And expect a reply back. Now there's a bug in that program there, because if your password is incorrect, you'll just end up hanging on the receive socket. So you're going to have to come up with some logic handling that branch there. Close the socket, close the context, and that is your request function for the public key on the client side. Now we have to set some options on the server side. We have to tell it that we need to set up a curve server. Hand it the secret key. On the client side, we tell it to grab the public key from the server. And then do the curve key pair generation. Set the client side public key and the client side secret key. And we should be good. Now let's run the program. And do a packet analysis in Wireshark. And everything is encrypted. So this is your bare bones curve encryption example up and running.